We're going to talk about heat production. The heat production is the main method by which LENR is studied, and it's the main witness to its actual occurrence. So it's very important to know how to measure the amount of power that the low energy nuclear reaction is actually producing. Nearly 1,000 papers have been published now describing heat measurements. So it's well established that this phenomena does in fact make excess energy. The problem is that dozens of calorimeter designs have been used to make these measurements, many of which are based upon designs that are personally constructed and are unique. Many times the calorimeter design has flaws, which has made it very easy for the skeptics to ignore the results. The field has moved far enough into reality that we now need a standardized design. We need a design that everybody can use that will produce values that are easy to understand and to accept, and then that can be compared. So I'll try to describe that. But first, let's talk about the basic mechanisms that are used to measure heat. There's three basic phenomena that are used: the thermal barrier, the heat capacity, the phase change. And then the one I'll discuss in some detail, I call the ideal method. And I will go into some detail about how that can be implemented. The method is quite simple. The implementation is very difficult, however, because of heat never wants to go where you expect it to go. So you constantly have to anticipate what it's planning to do in order to make the suitable corrections. If you'd like a nice discussion of the history of calorimetry, I suggest that you go to the website that's noted on this slide. Let's talk about the thermal barrier technique. This is called the isoperibolic method. And it consists of a thermal barrier, a semi-insulator, with a constant temperature on one side, and then the variable temperature in which the heat's being produced on the other side. The temperature difference across this barrier times a constant is equal to the amount of power passing through the barrier. Now, this is very simple. However, the value for C needs to be determined. It's you never know exactly what C is in your apparatus. Furthermore, there's no guarantee that the temperature is uniform within the apparatus, nor that the barrier is uniform. So there's a lot of variables that have to be taken into account when using this particular technique. But it's one that's been used quite frequently. It works very nicely when it's done carefully. But it does have the limitation that you cannot really study over a wide temperature range, because as the temperature goes up, by virtue of, let's say, heating a sample, then the problems increase, because that energy can go all different directions and through the walls of the apparatus, causing increasing error. Another technique uses the heat capacity of a material. This is called the flow method. Here, a fluid, usually water, is caused to pass through a pipe, and the heat is caused to pass into the pipe, causing the temperature of the fluid to increase. If the heat capacity of the fluid is known, which it is known in the case of water, times the flow rate, times the temperature increase that's been caused by the heat, that product is equal to the amount of power. And since we know the value of the heat capacity, and we know the flow rate, and we know the delta T, this becomes an absolute technique. That is, it does not require calibration. However, the heat energy in a real apparatus can go all different directions. It can escape in various ways. And so to be sure that the apparatus is in fact giving values that have meaning, it really needs to be calibrated. But it's also been used quite frequently to measure the excess energy from LENR, and it's a very reliable and sensitive technique. The heat capacity of the apparatus itself can be used. This is particularly useful if the source of heat is changing with time. The other two methods prefer the temperatures to have achieved a constant value before the values are calculated. But if the source of energy is changing with time, another technique is required, and that's described here as the adiabatic method. The temperature of the apparatus itself changes as heat is generated within the apparatus, and that temperature change times the mass times the heat capacity is equal to the power. Once again, we don't know the heat capacity of the apparatus. Furthermore, there's lots of different components in the apparatus, each with different heat capacity. And the temperature is not uniformly distributed among all of these components. So once again, the value of C times N must be calibrated. But the ideal method, which is called the Seebeck method, has come about because modern technology has provided a very convenient device that if a temperature is caused to occur across its thickness, it will generate a voltage in proportion to the amount of power that's passing through the thickness. And that's very, very convenient. You don't have to measure the temperatures. The apparatus does that automatically just simply by generating a voltage. And I'll go into some detail as to how that method can be used to make a useful device. The thermoelectric generators can be obtained from custom thermoelectric from the website shown. They come in all different shapes and sizes and cost. You can pick whatever is convenient. The thermoelectric converter also has to be bonded to a sink for the power that's passing through it, usually a piece of metal. And so a compound that has good thermal conductivity needs to be applied between it and the sink for the energy. That bonding material can be obtained from this other website. Now, the bonding material has sufficient stickiness that if it's applied uniformly to the thermoelectric converter, it will allow the thermoelectric converter to stick to the metal without any additional efforts to keep it attached. And that's very convenient because there are occasions when one of these may go bad or several may go bad and it's necessary to replace, and that's easily done, you know, if the only bonding is with this thermal paste. The apparatus starts with a box. And in this case, it's an aluminum box. All sides of the box, top and bottom, are water cooled. I'll show you that. And then the inside of the box is lined with the thermoelectric converters. Here's an example of the water path, the slots that were machined into a piece of aluminum, a ½ inch thick. And there's another piece of aluminum the same size that is then bonded using epoxy to this water-cooled aluminum part in order to seal the water. And all sides are done the same way, and the design is such that the water can pass from one side to the other. Here on the left is an example looking into the box that contains a thermoelectric cell, or contains a electrolytic cell in the center. On the left of that is a Geiger counter for measuring any radiation, and then this is a fan that is necessary to distribute the energy more uniformly within the box. The bottom of the box has been lined with the thermoelectric converters. The top of the box has not been lined, and you can see how it is constructed. The water passes into and out of the top through the hinges. On the right, you can see the completed assembly with the electrolytic cell inside, and then an additional box around the outside to further isolate the calorimeter from changes in room temperature. One of the beauties of this particular design is that any source of energy of any kind can be placed in the box with very little modification, or practically no modification at all, because the box does not care what temperature the source has, nor where it's located in the box. Here, the electrolytic cell has been removed, and the cell containing the deuterium or hydrogen gas, which can be reacted with the sample directly over a wide temperature range, has been put into the box. And we'll see a little bit more about that shortly. Here's the overview. Yours will be somewhat different, but this gives you a feel for all the other components that are necessary. Here's the calorimeter box. In this case, there is a laser that can shine through a small hole into the interior that can stimulate reactions within the box. The computer is here. I use the National Instruments data acquisition system with LabVIEW, which turns out to be very convenient. Various power supplies are needed. One, let's say, if you're going to use electrolysis, provide the electrolytic current. If you're going to heat the cell, another power supply, and then finally a power supply for the fan. All of the power that goes into the calorimeter is measured with the voltage measured at the calorimeter boundary and the current measured as a voltage drop across a resistor. And then below, you can see the source of pumped water. This water is at constant temperature, in my case, 15 degrees, and it has an uncertainty or a variation in its temperature of 1/100th of a degree. Here's an example of a box that was created by another group based upon my basic design. They made several errors that are worth pointing out. You'll notice that they caused the wires to pass directly into the calorimeter. That's not a good idea, because that allows heat to be carried into or out of the calorimeter that is sensitive to room temperature. It's necessary for any wire that leaves the calorimeter box to be thermally bonded to the box itself, so that the one end of the wire is now at a constant temperature. The calorimeter does not care whether some heat is lost to the box. It only cares that that be constant and independent of any outside source. So you do not want this kind of arrangement, because that makes the calorimeter sensitive to room temperature. You can't see that they did this, but they pass the water into and out of the top. It's better to have it pass into and out of the bottom, so that the water lines to the constant temperature bath are as short as possible, once again, to reduce the effect of room temperature. Now, if you're going to use an electrolytic cell, here's the one that I've used. Now, yours would certainly be different. The important part of this particular picture is shown here on the right. Most electrolytic cells are run at constant temperature to a large extent because the calorimeters that are used really only permit a constant temperature to be applied. This particular design allows a wide temperature range to be used because the calorimeter does not care what temperature the sample has or what temperature is in the electrolytic cell. So the electrolytic cell can be wrapped with resistance wire. A current can be passed through that wire, causing the temperature of the cell to be changed over a wide range. And it turns out that temperature is very, very important to the LENR reaction. The higher the temperature, the greater the amount of heat that this reaction will produce. And in fact, most failures, I believe, result because the amount of power that was produced at the low temperature, usually room temperature, 20 degrees C, was insufficient for the calorimeter to detect. But if they were able to heat it up to a higher temperature, the amount of power would have been easy to detect. So having the ability to change the temperature conveniently without any loss of accuracy is very important. And this is an example of such a design. This calorimeter needs to be calibrated. And the easiest way to do that is to simply heat the cell using that heating wire that you saw on the outside, but without the sample being present in the cell. So everything's the same. Everything within the calorimeter is unchanged, except it does not have an actual sample present. So this is the applied power to the heating wire, and this is the resulting Seebeck voltage. There will be a nearly linear relationship between the two. It's not quite linear, so it needs to have a quadratic equation to fit it. If the difference between the point, the measured value, and the calculated value based upon the equation is now plotted, you get these points. And notice that these points all lie within 5 milliwatts of zero. That's the random error that is characteristic of my calorimeter. And that random error is independent of the amount of power up to 30 watts. The calorimeter the temperature in the calorimeter is caused increase in steps. And this is the temperature of the inside of the cell that the sample would see. The temperature is maintained long enough for the calorimeter to come to constant temperature, which in my case is 100 minutes. But once that delay has been achieved and the constant temperature has been achieved within the calorimeter, the values now match zero, as they should. This is an example of excess power when an actual sample is placed in the cell. Again, the temperature is increased in steps all the way up to almost 300 degrees. And in this case, it's in a gas-loaded cell. An electrolytic cell can only go up to near 100 degrees centigrade, which does limit, but that does have a significant effect on the amount of power. In this case, it's gas-loaded. And you can see that the power, the excess power, increased as the temperature went up, and then it decreased. And there is a very fixed relationship between the temperature and the excess power. You can also measure other sources of energy if you wish, using this device with no modification at all. In this case, some tin was placed in the cell. Actually, only 8 grams of tin was placed in the cell, and the cell was heated. And as the temperature increased, it reached a melting point. And then once all of the sample had melted, the temperature continued to rise. This gave a value, essentially calibrated the temperature measurement. And this could be done upon cooling as well. It gave a slightly lower temperature. This difference is caused by gradients within the cell itself. You can see a break in slope occurring where the sample completely melted, another break in slope where it completely became solid. When this measurement was made more carefully, it could be the enthalpy of melting could be obtained, and the value calculated was within 1% of what is in the literature. So there are ways in which the calorimeter can be, in fact, calibrated independent of the LENR reaction if you care to do so. Well, the advantages are this calorimeter is very stable and it's independent of room temperature. It's very sensitive, plus or minus 5 milliwatts up to at least 50 watts of applied power. And it works over a wide range of temperature and power. One of my cells can measure the effective temperature up to 500 degrees. And there's actually really no limit if suitable designs are made. The measured power is independent of the sample temperature, temperature gradients, and the nature of the heat source. So you don't have to argue with anybody about the uncertainty of the various temperatures. It can be combined with the isoperibolic and the adiabatic methods. The temperature difference between the inside of the cell and then the outside of the cell, which is the environment within the box itself, that difference can be used and calibrated to on which a amount of power can be based. It's not as sensitive nor as accurate as the Seebeck, but if you're making large amounts of power, it becomes a very nice method of duplicating the value. It can be used with radiation detectors, magnets, lasers, all without the loss of accuracy. Anything can be put inside without affecting how the calorimeter works. It's simple to use, to calibrate, and to explain. Now, that last point is very important. The more complex a calorimeter, the less likely the skeptics are going to believe that the measured excess power is real. And so if you have a calorimeter that is very easy to explain and very unambiguous with respect to the various possible errors, you're well ahead of the game. Now, the only downside is that it's fairly expensive. The box itself would run at the present time about $5,000. It needs a computer, a data acquisition system, 3 power supplies, and a constant temperature water bath. So this is really only suitable for a laboratory that is well funded and tends to do essentially professional studies. If you're just a curious amateur or don't have a lot of money and want to see this effect for yourself, then you'll need to use a simpler design. Now, the next 2 slides list 40 papers that describe in detail various calorimeters that people, the individuals have used, some of which you might read and duplicate what they've done. But I would not recommend that for future well-funded professional work. But that information is available and you can read it at your leisure. So if you have any questions and would like to build a calorimeter like the one I've suggested, I'll be very happy to give you all of the details about my experience. There are a number of other issues that I have not discussed that you may want to know about rather than having to discover them for yourselves. So thank you very much.